Ready for a tree problem that trips up even experienced candidates? Binary tree maximum path sum is a pattern mastery 100 power question, and a favorite at Google, Facebook, and Microsoft for its tricky recursion and edge cases. Over 40% of interviewees make a mistake handling negative values or path splits. Let's ensure you ace it by breaking it down step by step. Let's master binary tree maximum path sum with the basic approach, ensuring you catch every tricky detail and never lose track of the recursion. Let's break this down. You're given the root of a non-empty binary tree. Find the maximum path sum, where a path can start and end at any node, and must contain at least one node. Paths can bend at a node, from left through parent to right, but cannot revisit nodes. Input: root node of a binary tree. Values can be negative or positive. Output: integer representing the maximum path sum. Here's a real-world example. Imagine a decision tree where each node's value represents profit/loss, and you want to find the richest sequence of decisions, even if that path bends through a parent. Interviewers might ask, what's the most valuable branch in a hierarchical project plan? Let's assess. What's tricky? Paths can go through a parent, taking both left and right children, but only at one split. Each recursion must return the single-sided max path, either left or right plus node, but must also update a global best if the whole V-shaped path through the current node is better. Negative values. Sometimes it's better to cut off a bad child by treating its max as 0. Think step by step. Traverse the tree with a post-order DFS. For each node, recursively get the max sum from the left child. Ignore negatives by taking max with 0. Recursively get the max sum from the right child, also ignoring negatives. The maximum path through the node is node.val plus left_max plus right_max. Update a global max if this path is better than any seen before. For the recursion, return node.val plus max left_max, right_max, the best one-sided path to use further up the tree. The global max may be at any node, not just the root. Let's clarify. Always take the larger of 0 in each child's path sum, so you don't decrease the path by including negative numbers. Update the global max at every node, as the best path may bend through it. Edge cases. All negative nodes must still return the least negative, biggest value. Skewed or one-sided trees should work identically. Single node trees must handle correctly. Here is the structure. Initialize a global variable, for example, max_sum equals inf. Write a recursive DFS function. If node is null, return 0. Compute left and right max paths, max 0, recurse left, etc. Calculate path sum through current node. Update global max if necessary. Return node.val plus max left_max right_max for parent recursion. After traversal, return the global max. Let's try to implement it using solution 1. Line-by-line narration. Line highlighted, class solution. We begin by defining a class called solution, which is simply the container where our functions will live. Pause. Line highlighted, def max path sum self, root. This defines our main function max path sum, which calculates the maximum possible sum of any path in a binary tree. The path can start and end anywhere, as long as it's connected. Pause. Line highlighted, self.max_sum equals float inf. Here we create a variable called max_sum and set it to -infinity. This gives us a starting point that's guaranteed to be lower than any real path sum, so the first real value will replace it. Pause. Line highlighted, self.max_gain root. This line kicks off a helper function called max_gain, which recursively evaluates the maximum gain from each node. It helps us build up the best possible path. Pause. Line highlighted, return self.max_sum. After all recursive work is finished, we return the highest path sum found anywhere in the tree. Pause. Small blue diamond emoji. Now the helper function. Line highlighted, def max_gain self, node. The max_gain function evaluates how much value a node can contribute upward to its parent. It's the engine that powers the logic. Pause. Line highlighted, if not node, we first check if the node is empty, meaning we've hit a leaf's child. Pause. Line highlighted, return 0. If the node doesn't exist, it contributes nothing to a path, so we return 0. Time complexity. Base case is 01. Pause. Line highlighted, hash compute max path sum with node as highest node, only one child side. This comment explains the next section. We're calculating the maximum gain that can come from each child, but only if that gain is positive. Pause. Line highlighted, left_gain equals max self.max_gain node.left. 0 we recursively compute the gain from the left subtree. But if the left side gives a negative total, we replace it with 0, because adding a negative value would only make the path worse. Time complexity, each node is processed once on. Pause. Line highlighted, right underscore gain equals max self dot max underscore gain node dot right, 0 and we do the same for the right subtree. We only take positive contributions, negative paths get ignored. Pause. Line highlighted, hash current max path sum considering both children, path through node. This comment tells us the next step evaluates a complete path passing through this node as the highest point. Pause. Line highlighted, current underscore max equals node dot val plus left underscore gain plus right underscore gain. This line calculates the full path sum if the path goes left child this node right child. It uses both sides plus the current node's value. Pause. Line highlighted, self dot max underscore sum equals max self dot max underscore sum, current underscore max has. Here we compare the best path we've seen so far with the new path that includes both children. If this path is better, it becomes the new global maximum. Pause. Line highlighted, hash return max path sum for parent to use, only one branch. This comment tells us the final value returned will only go upward to the parent, so we must choose one branch, not both. Pause. Line highlighted, return node.val plus max left underscore gain, right underscore gain. This returns the maximum gain the parent can use, the current node's value plus whichever side gives the highest gain. A parent can only extend the path through one child, not both. That's why we choose the larger of left or right. Pause. Final wrap-up. And that's how this algorithm works. It first initializes a global max, then computes the best gain from each subtree while checking every possible complete path through each node. By comparing every path and returning only the allowed upward contribution, we find the single highest path sum in the entire tree. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Now let's try another implement approach using solution 2. Line highlighted, class solution. We begin by defining a class named solution, which simply organizes our function. Pause. Line highlighted, def max path sum self, root. This function, max path sum, computes the maximum path sum anywhere in a binary tree. A path can start and end at any node, as long as it's connected. Pause. Line highlighted, max underscore sum equals, float inf, hash use list to allow modification in nested function. We create a list called max underscore sum with a single value. Negative infinity. Why a list? Because inner functions can't modify outer variables unless they're mutable, so the list allows updates from inside the helper function. This will track the highest path sum we find. Pause. Helper function. Line highlighted. Def max underscore gain node. We define a nested function called max underscore gain, whose job is to compute the maximum gain a node can contribute upward to its parent. This function is the core of the entire algorithm. Pause. Line highlighted. If not node, we check if the node is empty. If we reach a null pointer, there's no value to return. Pause. Line highlighted, return 0. When the node is empty, we return 0, meaning it contributes nothing to a path. Time complexity. Base case is 01. Pause. Line highlighted, hash compute max path sum from children. Ignore negative contributions. This comment explains the next lines. We're calculating the gain coming from each child, but we ignore negative values because they would decrease our path sum. Pause. Line highlighted, left underscore gain equals max underscore gain node dot left, 0. We recursively compute the maximum gain from the left subtree. If the left subtree is negative, we replace it with 0 so it doesn't drag our sum down. Time complexity, each node is processed once on. Pause. Line highlighted, right underscore gain equals max underscore gain node dot right, 0. We do the same for the right subtree. Only positive contributions matter for building the best path. Pause. Line highlighted. Hash current path sum through this node. Using both children, this comment signals that we're now computing the best complete path that passes through this node. Pause. Line highlighted. Current underscore path equals node.val plus left underscore gain plus right underscore gain. This calculates the full path sum if this node becomes the peak of the path, connecting its left and right gains. This path includes the node's own value, the best left path, the best right path. This may be the global maximum. Pause. Line highlighted. Max underscore sum 0 equals max underscore sum 0. Current underscore path. We update our global maximum. If the path through this node is larger than anything we've seen before, it becomes the new maximum. Pause. Line highlighted. Hash return max path sum for parent. Only one child branch. This comment explains the return value. A parent cannot take both children. That would create a split. So we must pick only one branch to extend upward. Pause. Line highlighted. Return node.val plus max left underscore gain, right underscore gain. We return the node's value plus the larger of the two gains. This represents the best possible path that can be continued by the node's parent. Pause. Back to the main function. Line highlighted. Max underscore gain root. We trigger the recursion starting from the root. This computes all gains and updates the global maximum along the way. Pause. Line highlighted. Return max underscore sum 0. After processing the entire tree, max underscore sum 0 contains the maximum path sum anywhere in the tree, so we return it. Pause. Final wrap-up. And that's how this algorithm works. It first tracks the global maximum using a mutable list, then computes the max gain from each node while updating that global path sum through the node that connects both sides. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Quick wrap-up on binary tree maximum path sum, a classic that exposes gaps in recursion, handling negatives, and path splits. We define the goal as finding the highest sum path anywhere in the tree. A path can start and end at any node, may bend through a parent once, and must include at least one node. We highlighted the two key ideas. 1. Each recursion returns a single-sided best path to its parent, and 2. At every node we also consider a V-shaped path using both children to potentially update a global best. Handling negatives by zeroing them out prevents bad branches from dragging down the sum. Our plan: post-order DFS. For each node, compute the best gain from left and right, never below 0. Consider the full bend through sum at the node to update a global maximum, and return the node's value plus the larger single-sided gain to the parent. We followed that plan end-to-end and ran it on LeetCode without errors. In tests, the approach captured both straight and bending paths correctly, handled all negative trees by choosing the least negative node, and passed the edge cases. The takeaway: separate the value you return upward, single side, from the value you use to update the global best possible split. Master that distinction and the hardest tree DP style problems get much easier.